Hello everyone, welcome back to 3 Deviations. So in today's video we're going to be talking about how we can manipulate an integrand so that we can make it something that we can indefinitely integrate with our table. Again, the table is the kind of harsh set of rules that we're being given for this part of Calculus 1. All of our integrals need to match the table, and that is going to change soon, but we'll talk about that later. So right now, in the last video, up to this point, we've been talking about how we can take integrals, indefinite integrals, of stuff like polynomials, trig, logs, and then a lot more stuff, a lot more elementary functions. And we've been learning about how to deal with this when they're added with one another, and then we've also dealt with these definitely as well, and of course that just means tacking on the last step of dealing with the fundamental theorem of calculus. And this was super easy because we could just separate the integrand. We just have integral of a polynomial dx, and then plus integral of trig dx plus, and we keep on going. We know how to deal with the separability of the sums of our integrands. So that makes it easy. But now we're going to talk about when we don't immediately just see those plus signs and say, hey, everything in between the plus signs matches the table. I could just look at the table, anti-differentiate it. It's good. Well, now we are actually going to talk about when it's not that easy, when we need to do a lot more manipulation before we can actually just take the integral. All right, so let's do that. So here's our example. So we are going to take the indefinite integral of 1 plus x over x squared. All right, so to do this first, what we're going to do is we're going to expand this. So there's a lot of algebra and a lot of trig in these examples just because we're using those identities. That's what these exercises are meant for. They're meant to make sure that our algebra and trig skills are still strong before we start dealing with more complicated things that we have in calculus here. So if we expand this, it's a little bit of algebra, a little foiling, but we will get the integral of 1 over x squared plus 2 over x plus 1 dx. All right, so now what we're going to do is we're just going to deal with each of these terms alone. So you have 1 over x squared, we have 2 over x, and then we have 1. All right, so for 1 over x squared, this is an integral that I think that you should memorize here. It ends up as being negative 1 over x. You can use the power rule to prove this, but I think it's good that you probably have it in your head that the integral of 1 over x squared is negative 1 over x. So that's the first one done. The integral of 2 over x, let's take the 2 out. That gives us 2 times the integral of 1 over x. Then that will give us 2 times the natural log of the absolute value of x. Then if I have 1, then that just goes to x. That's the easiest integral to take, apart from maybe e to the x. So of course just stays e to the x. Right, so now we can substitute back in, and that gives us negative 1 over x plus 2 ln absolute value x plus c. All right, great. So that is our first example done. Let's do another. So we are going to take the integral of the square root of x minus x over x squared with respect to x. All right, so to deal with this first, we're going to take this fraction and we are going to separate it. This is going to give us the integral of the square root of x over x squared minus x over x squared dx. Now what we can do is we can do a little bit more simplification, simplifying these fractions. That gives us the integral of 1 over x to the 3 halves minus 1 over x. All right, so now we can once again deal with this by parts, and we will end with our final antiderivative, with our final indefinite integral here, of 2 over the square root of x minus the natural log of the absolute value of x plus c. That is our final result for that. All right, here we go. We're going to keep on rolling through these. So we're going to take the integral of 1 plus cosine squared of x over cosine squared of x dx. Again, we're going to separate out this fraction. It's going to give us the integral of 1 over cosine squared of x plus 1 dx. All right, so immediately we should see this 1 over cosine squared of x. So 1 over cos squared of x. Now, what is this equal to? Well, we have the reciprocal identity, so that equals the secant squared of x. And this is in our table. So now we're going to have the integral of the secant squared of x plus 1 dx. And this is something we can do. We know how to anti-differentiate this. We know how to anti-differentiate that. And that will give us the tangent of x plus c. All right, so that is a good one. That starts rolling the gears about the trig. All right, so now let's do another one. We're going to take the indefinite integral of 3x minus 5 to the x dx. Right, so to do this, we're going to separate it. We're going to get the integral of 3x dx minus the integral of 5 to the x dx. Now these are both in our table as well. We know how to deal with general exponentials, and we sure as heck know how to deal with these monomials. So that's going to give us 3x squared over 2, or 3 halves x squared, however you like to write it. I sometimes switch between, minus 5 to the x over the natural log of 5 plus c. All right, so that is our answer for the fourth example. And then we're going to do just one more. We're almost done. This one's going to be pretty easy. Again, we're going to be dealing with a little trig. So we're going to take the indefinite integral of the secant of x times the secant of x plus the tangent of x. First, what we're going to do is we're going to distribute this guy, and that is going to give us the integral of the secant squared of x plus secant x times tangent x dx. Now, this should look awesome because we know that both of these are on the table. So we have secant squared of x, and then we have secant x tangent x. Right, so this immediately we know, we already did this one, that goes to tangent x. And then this one we also already know, that goes to secant x. Right, so now we are good. We can rewrite this as a final indefinite integral as the tangent of x plus the secant of x plus our arbitrary constant. All right, so that is some more dealing with our integrands. Hopefully prepared you for whatever elementary anti-differentiation or integration you're dealing with. In the next video, we're going to be talking about the net change theorem. That's basically how we can recognize the fundamental theorem of calculus and apply it to multiple situations where we have net change and want to deal with it continuously. So that is to come, and we'll see you then. Thanks for watching. See you in the next one. Bye.